So now if we relate what we know about energy, work, and power, with work also being another way of saying energy, energy is a quantity of energy that can be used or changed form or created. Power being the rate of energy at which energy is created, changes that energy changes form. We have to remember this. We have to remember total energy always remains constant. Because we have to remember energy is not created or destroyed, it can only change form. And hydraulic systems are a wonderfully useful system in which we use fluids that are liquid based in order to exploit the fact that we can make things move. We can quote unquote power things in order by using the forces that are built up in that pressure, but they are not a source of power. So when we say it's hydraulic powered system, it doesn't mean that that any power is not a source of power. It does not mean that a hydraulic system makes power anywhere. A hydraulic system exploits the fundamentals or the properties of a fluid in order to transfer energy from one place to another, in order to transfer power from one application to another. But that energy has to be added externally. And let's remember that energy is measured in joules, which is a kilogram meter squared per second squared. And it's equivalent to a Newton times meter, where a Newton is a kilogram meter per second squared times meter again. And let's just remember what power is. Power is the joules per second, or it is watts. And in the base SI units, that would be a kilogram meters squared per second cubed. All right, so hydraulic systems are very, very useful because they could transfer power, but we do have to add that power externally. So let's just review what linear translation means. We said that work is force times a displacement, right? And that is measured in newtons times that meter in which it displaced. Now, when we talk about displacement in meters, we're typically talking about a linear displacement, but we're going to get into rotational displacements as well. Let's look at linear motion, linear displacement, kind of the one that is a bit easier for our brains to understand. In linear displacement, if I'm traveling linearly, then my velocity is equal to the displacement. I've just gone from one place to another. That's my displacement. And it took me an amount of time to do that. I traveled some meters and it happened in some seconds. So this is our distance over time. This is if we're traveling linear, in our linear displacement. And another thing we know about linear displacement is that if I then divide this by time again, then that would be a rate of change of velocity. So I'm going to divide it by time again, and what I'm going to get is acceleration is velocity over time. So that would be our meters per second divided by another second, which would be in meters per second squared. So we have to remember these so that we can look at hydraulic systems and calculate what's going on. So that is another way of saying acceleration is of course in the calculus world, a small change in velocity over a small change in time would of course be acceleration as well, but we don't have to really get into that the instantaneous acceleration right now. Now, let's look back to practical things. We're saying hydraulics. We're going to look at our applications of all this physics, and we're going to say hydraulic systems are not a source of power, but they can transfer power. And so if we look at power, what is this power we say that hydraulic systems can transfer? We remember that power is a rate of change of doing work over time. And work is one way of saying work is over here. It's force times displacement over time. Force times displacement over time. So Newton meters over time, or kilogram meter squared per second squared over time. So kilogram meter squared per second cubed. Now, an interesting thing that I can do here then is I can take another color and I can look at this, distance over time. And I should remember what distance over time is. This is distance over time right here. Acceleration is distance over time. And this is distance over time. So distance over time is equal to acceleration. And I put a little vector on top of these things if they have sort of a force and a direction, a scalar and a direction. So I can conclude here then that if I multiply force by an acceleration, or wait a second, distance over time is not acceleration, it is velocity. And I just put this as distance over time. This is over time again. And distance over time was actually over here. Distance over time is over here. This is velocity over time. This is velocity over time. Excuse me for that. This is found over here. Distance over time. Distance over time, of course, is not acceleration. Distance over time and time again is acceleration. So force times distance over time. Distance over time, of course, is velocity. So velocity is distance over time. So force times velocity is equal to power. That is a very useful relationship. Power is force times velocity. I can measure velocity. I can apply a force. I can apply a force in a system. I can measure velocity. So I know how much power is being put in, or I can change this velocity to change the power input or output. And so this is translational. This is translational power. I can do the same thing in rotational power, and that is called torque. A torque is just the force that is applied in a tangential direction that's going to make is it going to make something rotate through a perpendicular, and it's applied at a perpendicular distance to make something rotate over time. So this is rotational power. Translational and rotational power, which will be useful to us in a hydraulic system.